Taking flight. It's the stuff dreams are made of. And it says something about us as a species, that we once looked at the birds soaring in the sky and said, bet we could do that. But in spite of our lack of wings and feathers, we did. And we didn't stop there. Once in the sky, we found a new limitation above us, space, a place where all the air ran out. And in spite of our very real need to breathe, we thought, bet we could go there. And we did, sitting on top of controlled explosions that we named rockets, all the way to the moon. Humans apparently don't like being told we have limits. But soon, the age of combustion rockets will be over too. They burn up their fuel too quickly, and using them for travel to the places we're thinking of going, like Mars, or even other stars, will simply take too long. And so, new technologies are needed. But what will get us there this time? For journeys that could take months, or even generations to complete, what solutions could help us bridge such gaps? The exciting part is, the answers are in development. And it turns out, these new ideas are even crazier than rockets. I'm Alex McColgan, and you're watching Astrum. Join me in this video as we explore the future of space travel, from the next generation solutions that are just around the corner, to the proposals that feel science fiction, but could one day become science reality. It's only in the last 100 years that humanity has truly begun to venture into space. On the 16th of March 1926, Robert Goddard, the father of American rocketry, launched the world's first liquid-fueled rocket on a farm in Auburn, Massachusetts. It may have only reached about 12.5 meters and was done to little fanfare, but this moment was the beginning of 100 years of chemical-powered rocketry that ultimately let man walk on the moon. Understanding where we came from is important in understanding where we're going. So let's take a closer look at chemical rockets. Here, thrust is generated by mixing some kind of fuel source, often RP1 kerosene, or other variations refined from crude oil with some kind of oxygen source. For instance, pure oxygen in liquid form in a combustion chamber and then igniting them. Hot things expand, and in such an explosion as this, they expand a lot. A chemical rocket points that explosion downwards. Then, thanks to Newton's third law, where every action has an equal and opposite reaction, the rocket as a whole goes up. Chemical rockets have been the key driving factor in more than 7,000 launches globally since the dawn of the space race in 1957. And even in space itself, chemical propulsion methods, whether burning fuel in thrusters or just spraying compressed coal gas out of a nozzle to get a little extra oomph at the right moment, are the primary way that probes and spacecraft have explored the various planets, moons and asteroids that make up our solar system. But chemical propulsion has a big problem. While it's very good at the short-term challenge of punching its way free of the Earth's gravity, a task that requires a large amount of force to be applied over the course of just 8 or so minutes, and a little light maneuvering to enter orbit around a planet, they are just not efficient, and so run out of fuel quickly. For instance, let's take a look at this Falcon 9 rocket, the kind favored by SpaceX in their hundreds of launches. While a Falcon 9 rocket has 549,054 kilograms of mass at launch, 395,700 kilograms of this mass is fuel. This leaves very little room on any rocket for the payload, or the part of the rocket you're actually trying to get into space in the first place. Why is so much fuel needed? The answer is in a chemical rocket's specific impulse, which is a measure in seconds of how much thrust you get for each unit of propellant. Think of it like the fuel economy of a spacecraft. While rockets are able to generate a lot of thrust, their specific impulse is quite low, never much higher than 500 seconds. They are like lightning-fast sports cars with really bad mileage. They can do very powerful bursts, but will then quickly need to top up at the nearest fuel station. Sadly, we don't have many of those in space yet. Which brings us to the next currently existing technology, one which has almost the complete opposite problem: electric thrusters. While not as commonly used as chemical thrusters, electric thrusters have seen use in missions like NASA's Dawn mission to the asteroid belt and by SpaceX's Starlink satellites. And by some metrics, these engines are impressive. Electrical or ion thrusters can have a specific impulse up to 10 times higher than chemical propulsion, allowing for far longer journeys or greater overall acceleration compared to their chemical counterparts. Electric thrusters come in many different types, but all work via Newton's third law, just like chemical rockets, pushing propellant out to push the rocket in the opposite direction. However, while chemical propulsion relies on hot reactions to produce their thrust, electrical thrusters, like the Hall effect thruster or the gridded ion thruster, work by creating electric or magnetic fields. Particles of noble gases like xenon or krypton are accelerated in these fields up to speeds of 140,000 kilometers an hour in ion thrusters, though less for Hall thrusters, and are sent flying off into space. When the particles accelerate one way, the spacecraft is pushed the other way. This is the advantage of electric thrusters in general. If you're accelerating your fuel up to 140,000 kilometers per hour, you're getting some really good mileage for each atom accelerated. When it comes to most thrusters, a key principle towards understanding them is momentum. And the thing with momentum is, if you don't know where to start with it, it can be hard to get the ball rolling. When I was studying at uni and was finding myself as stuck as an object at rest, I sometimes needed a helping hand to become an object in motion. For me, that didn't come from reading textbooks, it came from practice, testing my understanding with questions that forced me to engage my brain, which is why I really like Brilliant, today's sponsor. Brilliant has thousands of online lessons with interactive questions that get you thinking. It has courses on maths, coding, and even momentum, like this fun lesson that uses pool to teach physics principles. It's great for helping you study, whether you're young or old, a student or a parent looking to help their kids. Brilliant's courses are developed by top researchers at MIT, Harvard, and Stanford, so go try them out today by scanning my QR code or following my link brilliant.org/Astrum in the description below. There's a 30-day free trial, and my viewers also get 20% off an annual premium subscription, which gives you unlimited access to everything Brilliant has to offer. See if it gives you a little momentum too. Now, back to the pros and cons of electric thrusters. With all that acceleration, surely electric thrusters are just better then? Well, actually no. There is a downside, a significant one. You see, electric thrusters actually have terrible thrust. Think of it like putting your thumb over the nozzle of a hose. By limiting the hole the water is coming through, the stream of water coming out of the hose turns into a powerful jet. But removing your thumb to create a bigger hole does not mean you get an even bigger jet. You only have so much water to work with. For electric thrusters, the problem is similar, except instead of water, it's electricity. Electric thrusters connected to a solar panel can get plenty of energy if you leave them to run for long enough in sufficient sunlight, but you don't get that energy all at once. You have a limit on how much fuel can be accelerated based on the electricity you get in a given moment. So, how little thrust are we talking about here? How much can electric thrusters generate? It turns out, about the same amount of force as you'd feel from the gravity of a piece of paper lying flat on your hand. It can take days for an electric thruster to accelerate a spacecraft to just 90 kilometers per hour. And while it can get up to 320,000 kilometers per hour eventually, as NASA had considered doing on future missions to Mars, if there's any friction or opposition to its movement, an electric thruster won't ever get off the ground. Don't use one of these to try and launch a rocket. Electric thrusters are good in marathons, not sprints. Still, neither of these technologies are currently suitable for the types of travel that humanity wants to eventually do around the solar system and beyond. Because chemical rockets use up their fuel so quickly, they can't actually accelerate for very long and thus don't attain a good top speed. Electric thrusters have a good top speed, but accelerating is a slow process. And once humans start ferrying large numbers of crews, machinery, and raw materials to places like Mars, the amount of mass needing to be accelerated is just too much. And of course, electric thrusters will eventually run out of fuel too. So, what is the future of space travel? It's time to look at some of the contenders. Before I show you what NASA is developing, I want to give an honorable mention to a technology that I find really cool. Japanese company Obayashi is planning on finishing off a real-life space elevator by as soon as 2050. While not strictly a means of traveling through space, a space elevator is a fascinating alternative way to get something into space with a fraction of the energy costs that a chemical rocket has to expend. The principle behind them is simple. All you would need is some kind of anchor, a space station or an asteroid that was orbiting the Earth in a perfect geostationary orbit. Then you dangle a cable down from that anchor until it reaches the ground. Finally, just put an elevator on it. With the right counterweight in place, a space elevator would require very little energy to be able to lift things into orbit. You just have to hope that nothing snaps the cable. Obayashi wants to build their 96,000 kilometer cable out of carbon nanotube and aim to attach it to a 12,500 ton spaceport counterweight. It will take around 20 years to build the cable and reinforce it, but they say work should start in 2030. If all goes as planned, we could witness a space elevator on Earth that can carry 100-ton climbers by 2050. That would open a lot of doors for space exploration, and I imagine that lifting that cable into space will be quite the sight. In the meantime, NASA has been contemplating more immediate problems. They are hoping to send the first astronauts to Mars as early as the 2030s, so new technology will be needed by then. And they have come up with a solution. It turns out the future might be nuclear. The heat from nuclear fusion can be used to heat up a flowing liquid propellant, turning it into an expanding gas and jettisoning it out of the back of the rocket at a rate that is twice as efficient as a chemical rocket. This is called thermal propulsion. Alternatively, nuclear electric rockets would work by making electricity through nuclear fusion, essentially putting a nuclear power plant on a rocket and then using it to make the electric fields that are the basis of normal electric thrusters. Nuclear energy would provide more immediate electricity, so you could outpace normal ion thrusters with a large enough nuclear rocket. NASA hopes that nuclear rockets will be able to halve the journey time that is currently projected for a trip to Mars by doubling the specific impulse. These rockets wouldn't necessarily be launched directly from Earth's surface, you'll perhaps be glad to know. Although NASA toyed with that idea back in the 1960s with Project Orion. These rockets were intended to work by pulsing out repeated nuclear detonations behind the rocket and then just riding the shockwaves into space. That would have been quite the radioactive mess. It's probably for the best that NASA scrapped that idea. But if you start in orbit, nuclear rockets are generally safer for the population of Earth. Even if there's a catastrophic problem and the reactor melts down, there's no one nearby to suffer from the negative consequences of the fallout spreading, except those unlucky enough to be on the rocket, of course. Still, radiation in space is already a problem for astronauts that needs to be overcome. Just one trip to Mars could subject astronauts to 60% of the radiation limit that's recommended for their entire career, and that's assuming the journey only lasts 6 months. Some NASA plans see the round trip taking 2 to 3 years, because when flying from one moving planet to another, there's a lot of wiggle room when it comes to preferred trip length. Anything that reduces the time spent in space will mean less radiation for the crew and the passengers. That said, less radiation from space is only good if you can avoid getting radiation from your nuclear rocket. And nuclear rockets will need to be careful when accelerating near a planet's atmosphere, as due to the process of heating their propellant with nuclear sources, that propellant will be irradiated, which could over time lead to environmental problems. So while it's exciting that these spacecraft will be so big and powerful, great care will need to be taken with this technology. But what of further journeys? Even nuclear power can only get us so far. It may surprise you to learn that NASA has been exploring something called propellantless propulsion. And I think two of their projects in particular are very cool. I'm talking about solar sails and space tethers. NASA has deployed solar sails a few times now, though mostly for proof of concept rather than actual missions. They work by taking advantage of the fact that photons of light also carry momentum, so a light enough, large enough surface can catch all the gentle nudges emitted by photons streaming from the sun and use the energy to accelerate out on deep space missions for very low cost. NASA's Advanced Composite Solar Sail System was launched in 2024 and was originally deployed in space as a CubeSat. It then unfolded in space, stretching out 7-meter long arms to deploy a 9 by 9 meter square solar sail. It is currently in orbit around Earth as scientists monitor how effective its design is. Its flight has not gone flawlessly though, as sadly an arm became slightly bent during deployment, causing it to slowly tumble as it orbits. But NASA is still learning from the experiment. Future models could be larger than basketball courts, with 2,000 square meter sails, each side about 45 meters long if the design remains square. For deep space missions where no humans will be carried and budgets are lacking, being able to sail on cosmic light might be the most efficient way to complete a mission. A slight variation on this is the virtual solar sail or an electric sail. These sails are still in very early development, but rather than making use of a sail, they use electrically charged wires to do the same job. These wires stretch out and create a large electric field in the shape of a sail, which once again is gently pushed by solar radiation. This time not just because of momentum, but because of like charges repelling like charges. The company Sat Revolution has built AuroraSat-1 making use of this idea. There, the wires will act as a sort of solar brake when it comes time for the satellite to deorbit, the fields creating a sort of drag in the ionosphere itself, helping to quickly deorbit a satellite in a situation where atmospheric drag isn't feasible. And why use such virtual fields to only put on the brakes? NASA in 2024 released a report that discussed tether technology, effectively little more than long wires that protrude from a spacecraft. These can be used to exchange momentum from one spacecraft to another, but when the right current is passed through these wires, such tethers can push against the magnetic field of the planet, actually increasing a spacecraft's orbital altitude. Obviously, these types of craft would only work in the gravity wells of planets with magnetospheres, but the advantage of being able to boost orbital altitude in satellites is easy to see. You'd need less fuel to maintain a certain orbital position, extending the overall lifespan of the mission. All you would need is electricity to make it work, and a few solar panels would take care of that. But what happens if we want to go even further, beyond our solar system itself? The nearest star to our solar system is Proxima Centauri, which is 4.25 light years away from us. To cross that kind of distance, we would want the fastest craft available to us, so we would likely prefer an electric thruster over a chemical propulsion one. But even if such a thruster managed to get a craft up to 56,000 kilometers per hour, a speed attained by the Deep Space One mission's electric thruster in 1998, it would still take over 81,000 years to cross that distance. This would be far too long for humans to contemplate. Thousands of generations would pass before the descendants of a manned crew finally arrived. Obviously, thinking this far ahead, things start to get a bit theoretical. But what options are there for speeding up the travel time? Well, there's a few. Some are even attainable with our current levels of technology, while others are a little more outlandish, but a lot more fun. To begin with, there was a buzz in the news back in 2021 when NASA scientist Harold White claimed to have discovered a real, albeit humble, warp bubble. If true, this would have been quite the coup, as warp bubbles might hold the key to moving faster than light itself. Warp bubbles work by recognizing that nothing in space can travel faster than light. but there's no rule that says that space itself can't expand or contract faster than those speeds. Gravity causes a contraction to occur in space, so if you could somehow concentrate that kind of contraction in front of you, then create some kind of expansion in the space behind you, it might be possible to create a bubble with you in the middle of it that moved across space by changing the distance between things rather than by trying to close those distances. Effectively, it's like trying to circumvent a 30 km/h speed limit on a road by moving the road itself. There are a few drawbacks to such warp bubbles, namely that to expand space, you would need some kind of exotic negative matter to create the opposite of gravitational contraction of space-time. Sadly, we have never actually seen this kind of matter, and it's dubious it even exists. On top of that, such a warp bubble would need a ridiculous amount of energy, and some models suggest it needs more negative energy than the amount of positive energy that exists in the whole universe. So, warp bubbles seemed a long way off, which is why White's bubble was so exciting. Admittedly, he claimed that it was only large enough to be able to fit a 1 micrometer sphere, but proof of concept would be a huge step forward. Sadly, White's bubble was soon to burst. As other scientists started taking a closer look at White's paper, it became clear that he hadn't actually made a warp bubble, but had merely calculated something that looked a bit like warp bubble calculations if you squint. There was no experimental proof. White hadn't even been working on warp bubbles at the time, but rather Casimir cavities, a quantum effect that appears between two plates under certain wavelengths, and it was one of these that had some characteristics that were similar to what you might want to see in a warp bubble, which is a far cry from actually making a warp bubble. So, warp drives might still be one for the realms of science fiction, at least for now. But the last technology I want to talk about today feels a little more within reach. Part of the challenge of traveling between stars is acceleration. If you had infinite energy and could thus accelerate infinitely, you could vastly cut down on that 81,000 year travel time. But this is easier said than done. Carrying chemical fuel with you is not an ideal solution, as you will quickly run out of fuel without getting much acceleration. And electrical thrusters will also struggle, as solar panels drop in effectiveness the further from a star you travel. In our own solar system, the furthest out missions can realistically use solar panels is Jupiter, and even there, the missions that try that approach, such as Juno, have to have massive solar panels and accept 25 times less light than we see on Earth. In interstellar space, solar panels just wouldn't work. But what if you could get energy to order? Then you could use an efficient electrical engine and accelerate much longer after the sunlight ran out, which is why scientists have started considering beaming. By putting a large laser on Earth or in Earth's orbit, you could send a stream of photons directly to a receiver on the spacecraft, energizing it as it traveled. Or you could use electrons accelerated to near light speeds to do a similar thing. Or you could put a solar sail on the spacecraft and rely on the momentum of the beam to give the craft a constant push. A duo of researchers, Jeffrey Greason and Gerrit Broekhaug, published in the journal Acta Astronautica, calculated in 2024 that a probe the size of Voyager, pushed and energized by an electron beam, could reach 10% the speed of light. That would cut the travel time down from 81,000 years to a far more reasonable 40. Suddenly, getting humans to other stars becomes much more feasible. But of course, there are a few challenges to overcome here too. How do you stop the beam from spreading out as it travels? How do you make sure your spacecraft doesn't melt as it's constantly blasted by a giant laser? How do you keep the laser pointed exactly at the spacecraft that's traveling further and further away? But these feel like solvable engineering questions rather than hypothetical physics ones. There was a project back in 2016 called the Breakthrough Starshot Project that even aimed to implement this technology. It would use a ground-based laser array, at least a kilometer across, to send a tiny star chip into interstellar space. Sadly, the project petered out due to the daunting costs involved, but it showed that the idea is much closer to realization than warp drives. According to some engineers and researchers, if we were willing to spend the money, we could cut trips to Mars down to 45 days. So, whether by solar sail, electric field, nuclear power, or laser beam, or maybe even a warp drive, humanity is exploring many ways to get around in space. And once out of a planet's gravity well, the vast empty distances we aim to traverse require unique approaches and unconventional technology if we want to live long enough to see our destinations. But it's so fascinating living in what feels like the dawn of a new age, where this subject isn't just science fiction anymore, but humanity really feels like it could soon be leaving the cradle of Earth to reach for the stars. After all, staying at home would be accepting a limit, and as we know, humans don't do limitations. Have you ever wanted to ask us a question? Our favorite section of the newsletter is dedicated entirely to questions and answers. Just sign up down below and reply to one of our editions with anything you've been wondering about. It can be about space, science, or even how we make our videos. We love hearing from readers and featuring your questions in future issues. It's a simple way to join the conversation and be part of the Astrum community. So, if curiosity ever strikes you, make sure you're on the list and ready to send in your first question.